So it's my pleasure to welcome Ben Albo from Intel at IWOCL this year. Ben is one of the pillars of the OpenCL community. He's one of the OpenCL spec editors at Khronos. I've been working with him for quite some years nowadays. Ben is going to present us the state of the union for OpenCL. Thank you, Ben.
All right. Thanks very much, Bryce. And thank you, everybody, for being here. I am Ben. I work for Intel. Today, I'm literally, though, wearing the OpenCL shirt. I'm here to represent Khronos and the Khronos OpenCL Working Group. So this presentation is going to tell you what we've been working on for the past year, some plans for what we plan to work on between now and maybe the next IWOCL, and how you can get involved and participate. So one of the themes of my conference or my talk is kind of things that have changed in the last year or 5 years or 10 years. I went back in my memory and I gave a similar update 10 years ago at IWOCL 2015. So you can see a lot of things are similar. There's a lot of people standing around the food. You look, there I am in the middle. And if you don't get too close, I think that I look about the same as I did back then. But there are a lot of things that have changed, and we're going to talk about some of those in today's talk. One of the, I guess, benefits and curses of being one of the first talks is that I get to kind of set the stage for everything that Khronos does. So we're going to start up at about a 10,000-foot view, and we're going to kind of double click on down and zoom in and figure out what this OpenCL thing is anyway, for folks that may not know. So to kick things off, Khronos is an international nonprofit standards consortium that is open to any organization to join. And one of the cool things about Khronos compared to some other standards groups is that the standards that it produces are royalty free. So any developers can use Khronos standards for free. The kind of overarching theme of the APIs that Khronos supports is about enabling applications to access hardware acceleration. So that covers things like parallel computation, 3D graphics. There are other Khronos groups for things like virtual reality. There's a lot of companies that participate in Khronos. There's, I think, 160 members now. You don't need to count them all. And it's been around since about the year 2000. So it's been around for a while. It has members that are spread across the world, including many that are here in Europe. Most people, attending this conference are probably most familiar with OpenCL and SYCL, but there are some related APIs that Khronos is also involved in, such as the SPIR-V intermediate representation, OpenGL, and Vulkan for rendering. If we, again, zoom in just a little bit, Khronos provides a diversity of APIs for compute acceleration that are suitable to different markets and developer needs. And this slide tries to position them all and show kind of how they relate, where there are some similarities and where there's some differences. So we're going to start at the bottom and work our way up. Again, this talk is primarily about OpenCL, and OpenCL is a low-level API that enables software to execute on a mix of heterogeneous compute accelerators. So this would be your things like your traditional CPUs and GPUs, but then also some more, maybe less common hardware like FPGAs or DSPs or specific dedicated tensor hardware for AI, things like that. If we look on the left-hand side, Vulkan is an even more low-level API. It's primarily targeting GPUs, and both OpenCL and Vulkan can compile their small programs, shaders or kernels, to the SPIR-V intermediate representation, which they can then execute on the devices that they support. If we move our way up a little bit, SYCL and OpenVX are higher level programming frameworks that provide higher levels of abstraction. Tom's going to tell us all about what SYCL's been up to tomorrow, I believe. So I don't need to say much about that. The OpenVX is another kind of higher level framework that Khronos supports that has a graph-based abstraction that's common for vision and inferencing acceleration. It's especially used in the embedded markets. Then we have our third-party libraries, applications, some higher level frameworks. They can target either one of the higher level abstractions, or they can go straight to the lower levels of abstractions, and that's how they can get to the hardware. If we look at OpenCL specifically, again, it's a low-level standard for cross-platform parallel computation on diverse heterogeneous processors, things that can be found all the way from the biggest supercomputers to PCs like your laptops, mobile devices, and embedded platforms. It includes both a runtime API as well as a programming framework with C and C++ based kernel languages. And the basic idea here is, well, as long as you have an OpenCL implementation for that hardware, you can execute these programs on a diversity of accelerator hardware. Some of the things that OpenCL can do, it provides APIs to discover the compute devices that are on the system, to compile the programs for those devices, and then explicitly allocate memory and run the programs on those devices. Khronos, we love all of our children, but if we compare things like OpenCL to other APIs like Vulkan or SYCL, we find that some developers prefer the simpler programming interface, especially compared to Vulkan. It's a lot less code to get something to work through OpenCL. It has a lightweight runtime, and especially compared to the graphics shading languages, there's a lot more features like pointers, defined precision for math operations, things like that are important to some applications. Okay, so now that we've kind of got some background out of the way, this is more about the state of the union. How is OpenCL doing in 2025? And the short summary is that we believe OpenCL 3.0 continues to be a success. We continue to see new OpenCL adoption, and the API is continuing to evolve. We are still primarily developing new OpenCL features through extensions, and these are driven by the mobile, embedded, and desktop markets. Our extension pipeline includes extensions to support AI use cases, such as reportable command buffers, cooperative matrix to access dedicated hardware for matrix multiplication, and support for new AI data formats like eFloat16 and FP8. We're also actively looking at extensions to improve how memory is allocated and used in OpenCL. That's going to allow more applications to incrementally add support for OpenCL. We do continue to release regular updates to the OpenCL specifications. It tends to be about 3 to 4 times a year. Sometimes it's a bit more often, especially if we have some new extensions to publish. Sometimes it's a bit less often if we don't need to do a lot of spec maintenance. But we did do revision 18 of the OpenCL 3.0 specification just last week, which included a few new EXT extensions that have been incorporated into the main specification, plus the usual bug fixes and clarifications. One of the more exciting activities that we are seeing in 2025 is the open source activity around OpenCL. There are now multiple conformant open source implementations for OpenCL. And this includes some of the layered OpenCL implementations that layer OpenCL on top of other APIs. We've been tracking the number of OpenCL related GitHub projects for getting on close to about 10 years now. And we continue to see basically a linear growth in the number of projects on GitHub that are using OpenCL. Admittedly, we're not entirely sure what this means, but we are happy to see that the number keeps going up. It's not leveling off. If anything, it just keeps on growing. Neil observed that it's basically a ×3 increase in the past 5 years. And it's kind of neat too, the little elbow in that curve is about when we released OpenCL 3.0. So we've definitely seen a slight uptick, but since then, but it's basically been linear. We also continue to see robust traffic to the OpenCL device database on gpuinfo.org. We've added about 1,500 additional reports in the past year. Actually, we meant to check it this morning, but I didn't. We're getting awfully close to 5,000 reports in the database. So if we're not there yet, you could be the 5,000th report. As a reminder, the device database basically contains a queryable set of which OpenCL devices support specific OpenCL features. So if you're in the market for a new OpenCL device, you can check and make sure that it supports the features that you're looking for. Or if you're developing an OpenCL application, you can get some statistics about when that feature is supported, or the percentage of devices that support that feature. Or if you want to make a feature request to your favorite IHV, you can point to all the other implementations that support it and tell them that, you know, the other guy has it, you should have it too. Call to action: if you're a user of OpenCL and you look in the database and you don't see the device, it's really easy to just download the client, run it, and there's a button you can upload your device, and then that'll help out everybody else in the community to add the new hardware device to the database. All right, wanted to talk a little bit more about the trend we've been seeing in the industry. So this isn't just for OpenCL, it's actually across the industry of layering one API over another API. This was something that, you know, we initially heard about this and we're a little bit skeptical. It sounded a little bit scary. You know, why would you even want to do that? You know, just use the API directly. But we've actually kind of learned in the last couple of years that this is beneficial both to developers and to platform vendors. For developers, a layered API can enable an application to run on more platforms. So it expands the set of devices that can support an application. And for platform vendors, it's a benefit because it can bring support for a new API to a platform without requiring the support load of an additional driver. So if we look in the OpenCL column kind of down the middle here, most of the layered OpenCL implementations, at least the ones that we're currently tracking right now, are layering OpenCL over Vulkan and DX12. And if we look at a bit more detail about the layered OpenCL implementations, again, there are currently 4 that we're tracking. There may be others actually that we don't know of because there could be, but these are the ones that we're looking at. Again, 3 are used to layer OpenCL over Vulkan, and then there's the one on the right that's layering OpenCL over DX12. But it is pretty cool just to see the diversity of these implementations. You know, they're basically supporting most of the major operating systems: Windows, Linux, Android. It's also kind of neat to see some of the infrastructure that these implementations are using, especially on the compilation side, where a lot of these layered implementations are sharing infrastructure, heavily leveraging open source software, especially around SPIR-V. You can see even on the right-hand side, it was pretty wild to see that Microsoft is leveraging some of the Mesa support, SPIR-V support, to compile SPIR-V to the DirectX intermediate language. So that's pretty cool. One of the other kind of key changes that we've seen in 2025 is that many of these layered implementations for OpenCL are now passing the OpenCL conformance test suite, and they're shipping. So this kind of started out thought like, well, this is a neat science experiment or a tech demo or a proof of concept, but now these are actually shipping now. They're being used in production. So don't be surprised if you try to run an OpenCL application on your Android phone, if A, it works, and B, if it's using one of these layered implementations to layer OpenCL over Vulkan. OpenCL and AI. So AI seems to be important, especially for parallel computing and accelerators. So in the OpenCL working group, one of the questions that we frequently get is, does OpenCL support AI, or is OpenCL used for AI, or some variation of that question? And I'm happy to say that OpenCL absolutely is used for AI. This is especially true in the embedded and mobile markets. But the OpenCL use of AI tends to be indirectly. It's kind of used more behind the scenes as part of a vendor-provided inference engine. And we largely think that this is because AI is either moving too fast to efficiently standardize right now, or it's too difficult to use for some devices, or some combination of the two. On the framework side, we do see that most of the popular ML frameworks are gravitating towards higher levels of abstractions. So that means that they tend to prefer using SYCL rather than OpenCL. But we frankly don't think that's a bad thing. OpenCL remains a popular backend API for SYCL. So we've been thinking of this as largely another example of how OpenCL is used behind the scenes for AI. This doesn't mean that we've been resting in the working group though, and again, just to say it again, we do have a robust pipeline of AI-related extensions, again, that are specifically targeting AI use cases. This includes things like the recordable command buffers, cooperative matrices, and support for new AI data types like bfloat16 and FP8. So for the remainder of my talk, I thought I would be just reflecting on the past 5 to 10 years, describing some of the things that I've learned and how I believe they have affected the behavior of the OpenCL working group, and also why I'm excited, more excited now than I have been in a while about the future of OpenCL. I will say that while I was typing this up, some of these observations seem obvious in hindsight, but frankly, they have taken us a while to learn, and I don't think we've ever talked about them explicitly, especially not at IWOCL. And we do have the panel discussion. I think it's tomorrow evening. So as you're going through this, I do hope that this will inspire some good questions for the panel discussion tomorrow. So to start out, just a commentary about innovation versus standardization. And one of the things that I've learned is that working in the OpenCL working group is that we're frequently balancing conflicting goals. We do need to be thoughtful when we're adding new features to the standard to make sure that we're adding features that are useful to applications, that are broadly implementable, and that they integrate well with the existing standard. And then frankly, we made this mistake maybe about 10 years ago. I definitely think we've learned from that. All that being said, we want to encourage innovation and new features to reward the first movers and to make sure that we have solutions for emerging use cases. So the answer to this is extensions. I do have a bit of a love-hate relationship with extensions. In some ways, they're the cause of and solution to all of the working group's problems. But in all seriousness, they are an important part of the standardization process, and they are something that we have been doing more of, especially in the last 5 years. My call to action for really all of you is that if you find an extension useful, please tell us, because this does directly influence what we add to the standard. It can be a vendor-provided OpenCL extension. It can be a standard OpenCL extension, something that we should add to the core API that might be supported more broadly. But it could also be a feature from a different standard, or maybe sometimes a feature from a proprietary API. We really do listen to you, and if you can tell us what we can add, we can make sure that we get an OpenCL exposure of the feature and eventually work towards standardization. Another one that seems obvious in hindsight is that tests are super important. And I kind of been thinking now that a standard is really only as good as its tests. Several years ago, the OpenCL working group realized that we needed to improve the conformance test suite, also known as the CTS, and that we needed to do more of our conformance test development in public. And I'm pretty happy to see, this is a snapshot of the contributions to the conformance test suite over the past year. And it's basically as active on the conformance test suite in the past year as it almost ever has been. I think the only other time we were even close was when we were working on OpenCL 3. There have been about 300 commits in the past year, so almost one a day. And kind of more, I guess, encouraging than that, there have been over 40 contributors. So this isn't just one person that's been adding conformance tests. Beyond the pure contributions or the activity in the conformance test suite, I've also observed that several less visible changes in the way that the working group is operating, where we are doing things like writing test plans while features are in development, which has helped to identify issues and misunderstandings early. And it also helps to make sure that we have tests that are ready when the feature is published. So if you do want to get involved, again, all of our CTS development almost is occurring in public, and you can just go to our GitHub, write new tests. If you find some non-portability, you can file an issue, and we can keep enhancing the CTS suite. Touched on this a bit with AI, so I'm going to go through it pretty quickly. But it was an important realization that OpenCL usage is incredibly diverse. We still do have a lot of applications that are using OpenCL and OpenCLC directly. And I don't want to freak anybody out. We are going to continue to support them and to support them well. But we're also seeing a lot of applications that are using OpenCL indirectly, or using OpenCL kind of as a generic hardware abstraction layer to get to diverse heterogeneous hardware. Today, some good examples are SYCL, some of the vendor-provided inference engines, or OpenVX. But looking into the not so distant future, there could be other examples, including safety critical examples like SYCL SC, something like the ChipStar framework that compiles HIP to OpenCL, or even something like OpenMP offload. Frankly, I've also observed that the OpenCL working group has become a bit more humble. We have observed that many applications may want to support OpenCL, but they also are not going to rewrite or re-architect themselves to support OpenCL. And this means that we need to meet applications where they are, and we have been actively developing features that help to integrate OpenCL support into more code bases. Some examples of these are a lot of code that's written to either just run on a CPU, or maybe to run through other APIs like CUDA, are representing memory with pointers instead of CLMem handles. So we've been working to enhance the OpenCL 2.0 SVM support to support more kind of USM-like use cases, make SVM easier to use and also more performant, which would allow you to represent your memory with pointers instead of CLMem handles. We've also been working on external memory and external semaphore extensions to allow efficient interoperability with graphics APIs for rendering. And of course, we've also been enhancing and adding more support for SPIR-V as a compiler target for alternative source languages. So if you want to write your kernels in C++ or SYCL, or even some domain-specific language, or really anything that you can represent with something like MLIR or the LLVM framework, you can compile it to SPIR-V and then execute it through OpenCL. And finally, one of the more exciting developments, again, I've seen in 2025 is all of the open source development around OpenCL. Open source and open standards like OpenCL really do go great together. Obviously, this includes open source OpenCL implementations such as the RESTful work in Mesa, the enhancements to POCL and the One API construction kit, plus the layered implementations like CLVK and OpenCL on 12. But this also includes additions to the OpenCL ecosystem, like the OpenCL SDK, which is now developed in public, CTS, which we talked about previously, and then the ecosystem projects like the SPIR-V backend and LLVM, and I think we have a talk about that at IWOCL. Plus all the applications, high-level libraries, languages, too many to list, but we'll hear about a bunch of them at the conference. So all of this work is great for OpenCL users. It reduces fragmentation. It increases developer confidence in the API. We are rapidly reaching the point where you can basically assume that your computer system has a competent OpenCL implementation, which is great. But this also benefits implementers. So if you are looking to implement OpenCL on a new API, you can leverage a lot of this open source work to either add new features to OpenCL. Something like SPIR-V is practically trivial to support in OpenCL now. Or if you want to bring OpenCL to a new device, there's a lot of resources to bootstrap an implementation for that new device. All right, so we'll wrap things up. Very quickly, I believe the state of the OpenCL union is strong, and there are many reasons to be optimistic about OpenCL in 2025. Again, we've seen nearly all implementations moving to OpenCL 3, and OpenCL 3 adoption continues to grow. The OpenCL source work, I think, is especially exciting, both for end users and developers, to reduce fragmentation and to lower the barrier to entry, helping to bring OpenCL to new devices and use cases. When native OpenCL implementations are unavailable, the layered implementations enable access to the OpenCL ecosystem without requiring an additional driver. I think it has been pretty great to see the indirect usage of OpenCL through higher level models such as SYCL. And finally, I do think that we have a robust and active extension pipeline that solves real developer problems, including how to accelerate AI use cases. So to wrap things up, Moritz's call to action was great, but maybe just to expand on that, please provide your feedback. You can do that in many different ways. You can create issues on the OpenCL spec GitHub. You can engage via the Khronos Discord server. Khronos is on most social media. You can catch me in the hallways. Basically, we would love to hear from you. And this includes things like optional features, extensions used most often, what we could do to benefit the OpenCL ecosystem, et cetera, et cetera. So thank you, everybody. Very happy to be here. Look forward to hearing from you. And I think I have a few minutes for questions.
Not really a question, just a comment. You say OpenMP, it's maybe a future for OpenCL. In fact, it is already the case. I think Intel have an OpenCL backend.
Yeah.
And just put it upstream and everybody will be happy.
That's more of the comment, is getting it upstream, getting it more accessible. So it's not just an Intel thing, and so it's an OpenMP thing.
Yeah, exactly. But it would be fun to test the portability of your OpenCL implementation and
I agree.
different hardware.
Thank you.
Yeah, we've seen the slide with all of the different vendors and their OpenCL 3 adoptions, but some of them do not yet have OpenCL 3 adopted, AMD, for example. What do you think is holding them back?
Yeah, so I don't work for AMD. Yeah. I think it's mostly engineering resources, where they just, for whatever reason, have not decided to invest in that area. So then the best way to break through that is to write more software that uses OpenCL. And that will shift the priorities so that now that's a good place to develop your resource, to put your resources.
I mean, I can complement the answer. As client of AMD, one thing we can do is explicitly ask for OpenCL support for our GPUs. I make a point of doing that every time I visit a vendor, and I ask for the status of the OpenCL driver. Some of you are coming from computing institutions. I encourage you to do the same. Ask NVIDIA for an up-to-date OpenCL driver. Ask AMD for an up-to-date OpenCL driver. It does make a difference to the vendors when they hear their clients asking for something.
Yeah, maybe one more comment though, just an observation. And again, I'm saying this is very neutral, third party, not as an Intel employee. Some of the open source work is supporting AMD. So even if AMD isn't going to develop an OpenCL 3 implementation, somebody else may do it for them. I think RESTCL, I don't remember if they're conformant with AMD, but I know that they work on AMD and most things are very functional. But yeah, good question. I don't know that I have the answer.
I think we're out of time.
All right.
Thank you, Ben.